So picking up where we left off, this problem. So reminding you where we are. We had this solution that had barium and lead in it, and we wanted to separate those two ions. And looking at the KSP of lead and barium sulfate, we could see that they were pretty different. And so we can use that to separate them out, because we can say, okay, well, barium is going to precipitate at one point, lead is going to precipitate at another. And maybe there'll be some overlap there, but if it's small enough, it doesn't really matter. And there is like chemical reasons why we would want to do this. This isn't just a sort of made up problem. This is something that we would want to do at times in a lab. Okay, so we figured out their sulfate concentrations that would happen when they start precipitating. So if you're slowly dripping in tiny amounts of sulfate ion, little tiny bits at a time, your first one starts to precipitate out at 1.1 times 10 to the negative 8th molar. When that amount of sulfate is added, the barium starts to come off. It doesn't mean it's all going to precipitate, but that's when it starts. Meanwhile, the lead doesn't start until you're in the 10 to the negative 6th realm. So that's a pretty big difference, right? 1,000 times difference. So you should be able to add the sulfate in small enough quantities where you precipitate out the barium, a little bit, and then at some point say, okay, most of the barium is gone, pull that sample out of solution, and then start precipitating out your lead, okay? That's where we left off. Now, the next part of this is to say, okay, but how much barium is going to be left when I do that? Because when I say, all right, most of my barium is gone, I'm going to start precipitating out the lead now, there's still going to be a little bit of barium ions there. So in order to do that, so I just pulled these from the last slide, we want to figure out, okay, well, what do we know about the barium when the lead starts to precipitate? Okay? What do we know about the barium when the lead starts to precipitate? And honestly, we don't know anything about the barium, right? But what we do know is we know what the KSP equation for barium is. And when the lead starts to precipitate, we know what the sulfate concentration is too. Why? Well, because we figured that on the last slide. We know that it's 1.6 times 10 to the negative 6. That's the amount of sulfate that's going to precipitate out lead. So what we do is we fill that into the barium. Because we say, okay, well, at that point in time where barium has a bunch gone, we don't know how much. The only thing we really know in this equation is the sulfate concentration, because we know that that much sulfate is required to make lead precipitate out. So that may seem a little counterintuitive that you're putting the lead sulfate concentration into the barium one, but it's because we're not at that level where the barium has started precipitating. We're at the point where we've already gotten rid of most of it. So that's why you're taking it from the lead. You're saying this is when the lead starts to precipitate, how much barium is there? And then it's just division. That's kind of the hardest part, I think, of this problem, is noticing that make that logic leap, that what we know about the barium when the lead starts to precipitate is that sulfate concentration. And using that to say, okay, this is what our barium concentration will be, which means it's not a complete separation. Of that 0.1, I think, maybe 0.01, I would have to look again, molar barium that we had, we got almost all of it out. But there's going to be 6.9 times 10 to the negative 6 molar barium ions that's still left over in our lead. That's pretty small. It's probably pretty good. It's probably not something to worry about. But if whatever you were doing this for required like next to no barium, like that was even too much, well, then it matters, and you have to take that into account. So it's all just a matter of your specific thing. What does it matter to you? Okay. So quick review of this last little section that we did, especially since we did most of it last time. We had kind of two main parts of this section. We had using selective precipitation schemes where we just precipitate out one group of things, don't precipitate out the other. And we can use this to walk down a flow chart that would be given to you. I don't want to see a single one of these massive flow charts on your little note card. That would be a waste of space. Don't do that. I will give you any of the flow charts that you need. You would use one of those flow charts to say, okay, if I do this, what do I have? Okay, if I do that, what do I have? There's one way of using precipitation. The other way then is what we just did and saying, okay, I know that this is going to be precipitated, both of them are going to be precipitated out by this ion. So I'm going to add really tiny amounts first, and I'm going to get one to precipitate out and not the other one. and then I'll centrifuge it off, filter it off, somehow get that solid to go away, and then start precipitating out the next one. Okay, announcements, and then we get to do the last thing in this section. So don't forget you hopefully took care of your part 1 yesterday or a long time ago, but don't forget part 2 is due today. Sorry these were a little close. I just didn't want to make 18 part 1 due last Thursday when it probably should have been due. And then part 3 will be due Tuesday. We pretty much finished up everything you needed to do part 3 on Tuesday though, so you guys are set and ready to go on that. Don't forget the extra credit assignment if you feel like doing it. I know as you're getting further and further into quarter, the points on the extra credit is looking less and less important. I get that, it happens, don't worry about it. So the last thing then, the podcast for the nuclear chemistry. So I sent out an email saying, the last day of class, I have to go to this conference, and so I'm not going to be here. So you guys kind of had 2 options for what to do. And that was either have Paul give the normal lecture, do nuclear chem, talk about all of that stuff, or let me podcast that since those are my lecture notes and trying to have somebody else work off my lecture notes can be a little rough. Let me podcast all that and have Paul do review. So you guys voted on the let me podcast it and have Paul do review, which I think was the good choice. Mainly just nuclear chem is a lot of kind of me rambling about really cool things, and that's a lot easier to do when you're rambling about things that you've chosen to ramble about. So that'll all be podcasted. I have like 3/4 of them done and up. The only thing I have left to do is radioactive decay. So you guys can start doing that, watching it whenever you want. It's technically meant for like the last day of class. So it's its own separate little package, meaning that you can kind of stick it wherever you feel like it. So if you have a spare like 3 days and you want to hit nuclear chem, get that done and out of the way, go for it. If you want to wait till the last day of class, wait till the last day of class. That's when we were going to cover it. Meanwhile, Paul will do a review the last day. So, all right. So last thing. This is not so much this section on its own. This is like a combination of this section, acid-base chemistry, combined together. So this is my little chance to play dentist and explain to you why dentists say the things that they do. They probably don't know, quite honestly. They're telling you things that they know that if you do is going to either help your teeth or hurt your teeth. I get to tell you the why part of it. Okay, so here's our kind of learning outcomes. We want to connect in KSP and acid-base chemistry, and this does a really nice job of it. And so we'll talk about some of the reasons for preventing tooth decay and why they work. The why here is important. Don't eat sugar. Most 8-year-olds will be able to tell you that. That's important, yes, but we want to know the why part. Okay. And then talk about why we do the things that we do to prevent tooth decay, because that's important too. Again, focusing on the why part. We all kind of know that there's certain things that we should be doing, and we care about the why part. And yeah, these are all based on solubility and acid-base chemistry. I do apologize for the grossness of the next picture. Okay, so we want to talk about why does tooth decay occur? How do you prevent it on your own? Because back in the day when when our ancestors were evolving, we didn't have dentists that we went to every single year or so, or twice a year. So how do our bodies naturally prevent this? How can we survive to like 25, 30 years old when we get eaten by a lion without brushing our teeth? And then how do we actually make this last a little bit longer so that now that we don't get eaten by lions at age 30, we can keep our teeth until we're at least 70, 80. So first off, how does it occur? Okay, there's like lesson number 1 in what you don't eat a lot of if you don't want to have tooth decay. What's that? Sugar. Oh, okay, so sugar eats away your teeth. So if you like put a tooth in sugar water, it would eat it away. Is that what happens? Sugar's not corrosive, right? Sugar doesn't eat things away. So what really happens? Why can't we eat sugar? It's not the sugar that's the problem. No guesses? No one wants to feel ridiculous? No? Okay, fine. Wait, what? Yeah, go for it.
Is it, does that have to do with like how their polarities?
Not the sugar's polarity. So what else do we have a lot of in our mouth? We have teeth. This is a super appetizing thought. Sorry for anybody who decides to bring lunch to class today, I apologize. So let's look at this. This is actually the decay process that happens. Okay? So this is your tooth enamel. This is actually what decays it. What is this? What is our like random H plus? What are we denoting? What did we denoted it as like always? What's H plus mean? Acid, right? So that's why you're not supposed to eat acidic things either, right? They tell you, don't drink soda, don't have too much of pretty much anything that's acidic, which is a lot of our drinks. But there's something else that does this. I'm missing a picture. Hang on a sec. Something got out of order. Sorry about that. We're going to do this first. Okay. So it's actually the bacteria that do it. Sugar doesn't hurt you. You could eat like 10 pounds of sugar for breakfast, lunch, and dinner. Your teeth would be fine, as long as you ate it really quickly. So like you can't sit around and eat the 10 pounds of sugar and take 4 hours. You'd have to eat it in 10 minutes and then be done with it for the day. Lunch, 10 minutes for 10 pounds of sugar, be done with it. Don't do that. You'll die of diabetes. But like this is not medical advice. This is dental advice. Your dentist would be happy with you, except that you could never see them because you couldn't get out the door. But your dentist would be cool with it. It's the bacteria that are the problem. So what happens is you can't have it constantly sitting around on your teeth, because here's what happens with the bacteria. This is another chart that's just FYI. Do not memorize. Do not write this on your card. Do not worry about it too much. But I want to show you what happens. So this is a breakdown of bacteria metabolites. Again, don't freak out about this. It looks scary. That's not what I care about. What I want to show you is these things that I point out. Look right here. What is that? What do we call that type of molecule? Carboxylic acid. What do we call this? Carboxylic acid. What do we call this? Acid. What do we call this? Acid. Acid. It's like all carboxylic acids. Like everywhere you go, there's a carboxylic acid on one of the chains. Okay? So what's actually happening is not that the sugar hurts you, it's that the bacteria that live in your mouth hurt you. So if you could get rid of all the bacteria in your mouth, you could eat all the sugar you want, as long as you want, throughout the entire day. And again, your only real concern is diabetes, heart disease, and every other medical condition in the world. But your teeth will be gorgeous. Okay. So that's why you can't eat sugar. Because honestly, the advice to not eat sugar for your teeth, if you really think about it, doesn't make a lot of sense. Sugar isn't harmful when it comes to decaying things. It's not going to like break apart a plastic bottle. It's not going to break apart any sort of bottle, really. It just hangs out and doesn't react. The bacteria are the problem because they make the acid. It's all kind of based on acid. Okay, so next thing. Well, how do we actually keep ourselves from, like if you go back 10,000, 20,000 years, how did we keep ourselves from our teeth decaying away when we were 10? What did we do? We still do it today. And this is actually where a lot of preventative measures come in, where you wouldn't think about it. We drool. We have saliva. So this is the cutest drooling picture I could find. So this is actually what prevents tooth decay. If you think about it, our bodies do tend to start falling apart at about age 30 or so if we're not pretty careful. And that is because from an evolutionary standpoint, that's where things kind of go downhill. And we don't really need to live anymore because we've had a few kids. This is what actually can stop that on its own for a very long time. This is why even with not taking care of your teeth at all, you can usually keep them until your 30s or 40s without really dental hygiene. And that's cool, because that's needed at some point. Now, how does this actually work? Your saliva has a bunch of those two components in it. What are those two components? Not so much their names, but in terms of like acid-base chemistry, what are they? Yeah, it's not only a buffer, but they're both in some ways weak. Weak what? Can they pick up hydrogens? Or let's look at the phosphate itself. Can that pick up a hydrogen? Yeah. Can the HPO4 pick up a hydrogen? Yeah. So they're both in their own ways weak bases. If you make it in an acidic environment, those will help buffer that system. Those will pick up hydrogens for us. And if you have a healthy system and you measure the pH of your saliva, it should be basic. If you measure the pH of your saliva and it's acidic, you may want to look at your health a little bit. You can measure it with pH strips, actually. It's kind of cool. If you go into Amazon, they have like health test strips, something or other, the big long stupid name. All it really is pH paper. It's even orange like pH paper. It's the exact same stuff. Okay, so how do we prevent this in other ways? How do we actually take care of this and make it so that now we don't live till 30 anymore? We live until we're much older. Ignore that picture for now. And we need to keep our teeth until we're 70, 80, 90, 100. You know, in a couple decades, maybe we need to keep our teeth till we're 120, 130. How do we do this? So I came up with 3 ways. What do we think? How do we keep our teeth good? So what's the one thing you do every single day? Brush your teeth. Okay. What spoiler is here for you? Fluoride treatments. That one's cool. We'll see how that one works in a second. What's the other one? This one's a little bit trickier. I think I heard it. I think commercials. What are they trying to sell you off this? Sugar-free gum. Now, sugar-free gum is kind of an interesting one because it turns out the commercials are not full of just trying to sell you things. They're actually correct here. There's a reason why dentists recommend it. So let's talk about why for each one. Toothbrushing. This one's the simplest. Why does this work? It removes bacteria. It removes bacteria and it removes food. This is just like a purely mechanical thing. Okay, you get rid of the bacteria that's eating the food and you get rid of the food. Perfect. This one is not fun from a chemistry standpoint. These two kind of are. What about the sugar-free gum? This is the kind of mediocre as from a chemistry standpoint one. How does this one work? Yeah, it makes you have more spit. So yes, that's not exactly appetizing, but it helps add more saliva to buffer any acid you have. It's why it's good after food, because it can kind of counteract all the acid that's sitting around from the food and the drinks. Now, fluoride is the one that I think is the coolest from a chemistry perspective. So if you're doing fluoride treatments, and it's not just, hey, I'm brushing my teeth with it or I'm drinking water that has some of it, what do you have to do? Is it like a fast, you throw it on your teeth, spit it right back out? You have to let it sit there, right? So I think they still do this in schools where they like make you sit there and they put a timer on, or if you have the Act mouthwash, all of that. This one's the coolest, I think, from the chemistry perspective, because what this one does is it actually changes the enamel. So this is enamel. This is normal enamel as is with H+. Okay? This is what happens if you put acid on teeth. You get this. Those are all aqueous. That should be aqueous, sorry about that. These are all aqueous. These are not enamel anymore. You just eroded your enamel away. But what fluoride does is it comes into this OH- and it says, okay, OH-, I'm going to replace you. And I'm going to put an F there. So when you're sitting with it on your teeth, you're sitting there replacing the hydroxides on your enamel with a fluoride. You say, okay, why do I want to do that? Here's where the KSP stuff comes in. What do you notice about the KSPs here? Which one's smaller? The one with the hydroxide or the one with the fluoride? The one with the fluoride. This one's a smaller K. So since it's a smaller K, is it going to dissolve easier or less easy? Less easy, right? It's going to be harder to get it to dissolve. So you're going to need way more acid to be able to get something, your enamel with the fluorine off, than it is for your enamel with the hydroxide off. And you have to do this repeatedly because eventually what will happen is all the fluorides will get replaced with hydroxides and then you're back to this. So you do this, once a week, once a month, whatever, how often you do it, and you're constantly replacing the hydroxides with the fluoride, and then the fluoride is harder to dissolve than the hydroxide version. So you lower the KSP of your enamel, which is kind of cool. Okay. So our quick review on this. Sugar on its own is not harmful, right? All of our tooth decay processes, our enamel process, this is with acid. And there's another really kind of important chemical aspect here that I sort of snuck in, and that's the fact that there are a lot of equations where an acid reacting with something will make it dissolve much faster than it would on its own, okay? So if you have an acid that is dissolving anything that has a hydroxide in it generally, it'll kind of force the equation a little bit more to the right each time. And we can see that with the enamel. So we can combat this with buffers, which our body does completely on its own, give it a little boost on the buffer situation with some gum, or we can actually lower the KSP of our enamel completely and say, okay, we're gonna lower the ability of you to dissolve by like 10 by 10. It's quite a bit. And that is the end of this chapter. I'll give you a second to pull up your other notes if you need it. Okay, we're going to start this one off with just kind of an overview of where we're going on electrochem. This is the first time in this class, now that it's week 8, where we finally kind of get to start over on a new storyline, right? Up until now, it's been like, okay, we had all of these equilibria. And then we had this special case of equilibria that were acids and bases. And then we had this special case of acid and bases with equilibria in titrations and buffers and KSPs, but it was still the same storyline. This is kind of a, okay, we're still gonna use all the things that we learned before. We'll have equilibria, we'll have thermodynamics, we'll have all of the things that you've done in 1A, 1B, and 1C, but it's kind of a new storyline. Oh, and I like this quote. So someone said to Michael Faraday, why would we ever want to use electricity? And this was his response, well, one day, sir, you may tax it. I like this quote because there's a lot of science that we do that people say, there's no point to this. What are you going to do with it? There is no way that the person who posed that question had any concept of these lights or any concept of this projector or like no way that they had an idea of this. Like even the people who made Star Trek kind of messed up the phones. And that was way later than this, right? So there's just no way that they can imagine that this is what we could do with electricity. So this quote has a lot more implications, I think, than just, hey, it's a cool quote about electricity. It's a quote about science. It's a quote about how basic research, basic science that we don't have any idea where it could lead to is still really, really important. And this is especially important for like physics and math and the physical chemistry side of chemistry, where it gets very little funding, it gets very little advertising, it gets very little anything unless it has to do with invisibility. Invisibility, for whatever reason, people kind of jump on. But it's important to note that we have no idea where a lot of the science actually goes, and this is a really good quote to show it. Because I don't know about you, but I would not be giving up electricity anytime soon if I had the option. Okay, moving on. That was my little tangent for the day. What are we going to do in this chapter? Okay, a whole bunch of things. And I think you'll like most of it. It should feel like a little bit of a reset. So we'll talk about redox reactions. All of our electrochemistry are going to be what we call redox reactions, where we have something that is being oxidized, we have something that is being reduced. Much like in acid-base chemistry, where one thing was an acid and one thing was a base, and you had to have both, even if one of them was just water. You had to have one of each for it to happen. This is going to be the same thing. They're going to be linked together. One thing will oxidize the other thing. One thing will reduce the other thing. These reactions are a little bit different than all the other reactions that we have done. All the other reactions that we have done, just all that really mattered is, can we balance the species that are in reactions, right? Can we say, I have this many of this, I have this many of this, I need to make sure that products and reactants are balanced. These are a little bit different because you're transferring electrons too. And so we have to learn to account for that. We have to learn how to balance it and account for those electrons. Once we do this, we can use those electrons for something. We can say, okay, these electrons are going to be able to do work for us. Or maybe we're going to pump electrons into the system for various different reasons. Lots of reasons we want to do that. We need to know things about, well, how much energy are we going to get back? How much energy are we going to put in? And so that's going to lead into cell voltages and Gibbs free energies and equilibrium constants and things of that sort. We also need to figure out, when is something actually going to undergo a redox reaction? sure, we can hand them to you, and we can say, this is how we do this, this is how we do this, but you should be able to pick them off a table too and say, oh, this will happen, this won't happen, this will happen if we actually put some energy into the system. And then, of course, all the things that we're going to actually try to figure out what to do with them. So at the end of this, what we would like to be able to do is explain fuel cells. which are a little bit different than normal galvanic and redox cells, but they're still electrochemistry, they're still really important. We'd like to figure out why rust happens, and more importantly, how to make it stop. Because we don't want things to rust, right? We put a lot of time and money and energy into making all these metal things that need to be outside or in water, and we don't want them to rust. It's not actually as big of a deal here, except if you own a boat. But in places, in the Midwest, Northeast, that are constantly soaking your cars in water and air, it becomes a really big deal, and your buildings in water and air. And then a bunch of cool other things along the way, but those are kind of the really big ones. We are not going to have time for this. That's fine. The other things are more important to you guys specifically, but know that battery research is really cool. And right now, we are kind of at an explosion of it because we need it. The reason being is most of our alternative energy solutions, the reason why they kind of fail for us right now is batteries. Okay, wind energy is great, but what happens when the wind dies down? If we don't have a really good set of batteries backing that up, we have a problem. Solar energy is great, but what if we have a week of clouds? We need really good batteries to back that up. Teslas are awesome. But what if you want to go across the country and you have to go through Oklahoma and Kansas and Texas and all these places that do not care about the electronic cars as much as we do, nor have the money to really support that kind of system? How do you do it? Batteries. So this is like a ridiculously important thing that we're really kind of on the cusp of right now. So it's worth, even though it's not super important to the majority of majors in this particular class, as human beings, it's not a bad idea to go, get on a Wikipedia tangent with it or something. Okay, so what is electrochemistry? Good, important place to start, right? What is all of the things that we're going to talk about? This is our main definition, where electrical and chemical energy are meeting. Where now we can take chemicals and we can get electrical energy out of it. We can take electrical energy and we can get chemical things to happen because of it. That back and forth is our main definition of electrochemistry. One thing is always going to be oxidized, one thing is always going to be reduced, and in that process, electrons get transferred. That electron transfer, if we separate it and we put something in the middle, we can use to do work. We can use to make those electrons do something. So here's an example of one. So this is zinc, copper. So zinc is the little blocks, the little solid in the solution. Copper is the aqueous, the blue. The sound doesn't matter. And when you put those two in solution together, you end up getting a spontaneous redox reaction. So they just swirled it to hurry it up because it was taking too long. So they swirled it, moved things around a bit, and you get this automatically happening. And if you stop swirling it for a minute, you can see, you can see this like coppery color. Well, that's because you just made copper solid. You've taken copper from the solution, you've put it where the zinc was. You just kind of replaced them. And now the zinc solid is actually going into solution. If you put enough of this in here, you could actually change the whole color of the solution too, but it would take a lot. So that's electrochemistry. You're changing the charges, you're changing the oxidation state. It's different than a normal reaction. Okay. So now we get to start into the favorite section of all the chapters, which is to go through all the definitions that are important. This has a lot of sort of memory tricks in it for remembering which one is which. It also has a lot of what feels like double negatives. So be really careful with how you say them. You'll also probably notice that I slowed down my speech quite a bit so that I don't mix them up. It is pretty easy to do. Okay. So these are all the things that we need to be able to define. Oxidation, reduction, oxidation number, the reducing agent, the oxidation agent, and then be able to find the oxidation number for everything. This is like step one. Do not go past this until you can do all of these, and not just do them, but do them instantly. Do them second nature, where you look at a reaction, you say, okay, oxidation numbers, blah, 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 done. That's my oxidized species, that's my reduced species, done. Until you can do it about that, okay, you're gonna take a little more time on the numbers, but until you can do it that quickly, don't move on, because this is the foundation of everything else. Okay, so what are these? We're gonna use this as our very simple version, and then we'll do some harder ones. Oxidation number, it's kind of step one. This is, I love this definition too. Imaginary charge if the compound was broken down into ions. This is because some of these things that we're going to be looking at are not really what you would call ionic, or at least the parts that we're looking at wouldn't be. So it's as if everything had a charge. This is not quite the same thing as formal charge. It's a little different. So there's some rules for figuring this out. The oxidation number of an atom in its elemental form is 0. So any of your metals, that's just the metal. Any of your diatomics, like chlorine, bromine, iodine, hydrogen, those, it's the diatomic that's 0, not the thing on its own. So of these, we look at sodium, that's an element in its natural form. It's just a solid metal. That one is 0. Chlorine is a diatomic. So its elemental form is actually Cl2. That's 0. Okay? Now, the next part. A monoatomic ion is equal to its charge. That means, okay, if you have any of the ions that you know that sulfide is a -2. Sulfide, if you see it, it's a -2. You know that fluorine is a -1. If you see it, fluorine -1, that is, like sodium fluoride or potassium fluoride, something like that, you know that that's a -1. All the ions that you already know, you know their oxidation number. So in this case, that tells us sodium is what? What is the charge on sodium? +1, right? It's in that first group, so it's +1. And what's the charge on chlorine? -1. So their oxidation numbers are +1, -1. This does get a little more complicated than that, but that gets us started. Okay. Oxidation numbers of a molecule must add up to the oxidation number of the whole thing. So for sodium and chlorine, well, okay, it's just sodium and chloride, so that not much to do with that. But with the sodium chloride, what's the charge on sodium chloride, the whole thing? 0. That means that the charges on the species have to add up to equal 0. On something like sodium chloride, that's not super helpful or super needed, because we know sodium, we know chloride, we've got that. Where that comes in handy is things that have more than one oxidation number. Copper can be +1 or +2, right? Or manganese has a bunch of different oxidation states. It's useful when we don't know what the other species is. So let's do some extra practice with those. Oh, and that's just what I already said. So you use this to find ones that you wouldn't know otherwise. So like these. So our first one, we have sodium chromate. We know some of these. What do you think the oxidation number on sodium is? It's +1. We have 2 of them, so careful note on how you say this, because this always gets a little bit confused. The oxidation number on sodium is +1. Don't say that it's +2, okay? Keep it as +1. There are 2 of them, and so for the sake of figuring out what the chromate's going to be, or what the chromium is going to be, we need to say, okay, there's 2 of them, so it's a +2. But the oxidation number of sodium is still +1. See the difference? All right. Now, we don't necessarily know chromium. Chromium has a few different oxidation states, so we can't do that one right away. But we know oxygen, right? What does oxygen like to have? There's a few exceptions, but almost always, what is oxygen? -2. So now we know oxygen, and we can say, okay, the oxidation state on oxygen is -2. There are 4 of them, which means that we are up to a -8 charge there. What is the overall charge on sodium chromate? Is there any charge on sodium chromate? The whole thing together? No, it's 0. So when we get done, all of this has to add up to 0. Is it added up to 0 right now? It's added up to what? -6. And there's only one other thing here. What's the only other thing here to make it equal 0? Chromium. So what does the charge on chromium have to be, or the oxidation state on chromium have to be? It's got to be +6. Okay? If there was 2 chromiums, there's not, and it wouldn't make a lot of sense here, but what if there were? If there were 2 chromiums, what would the charge on chromium be? 3, right? Each one would be 3 to add up to 6 total. Okay. Now let's do manganate. Notice manganate, it has a charge. So what are they all going to have to add up to with manganate? It's going to add up to be -1, right? Okay. We don't know manganese because manganese has a few different options. But we do know oxygen. What's the oxidation number on oxygen? -2. So the oxidation number on oxygen is -2. There's 4 of them, which means total right now we have a -8. And we want it to be what again? -1. Not 0, we want it to be -1 because the charge on it is a -1. So what does the manganese have to be in order to make that happen? +7. That is sort of step number 1, but don't move on, don't pass go until you can do this, okay? And have it be relatively second nature. Just sit down with a book and find any compound that's in the Redox section and just go through and practice and practice and practice. It should be fast, it should be second nature. Okay. Along those lines then, there's a bunch of definitions that we need to use to talk about this. Okay? Because we don't want to have to, when we talk about whether something is happening, we want to be able to use common language between everybody, and that's where all these definitions come in. And first off, oxidation and reduction. So oxidized is going to be losing an electron or increasing the charge. Okay? It loses the electrons, it gives away its electrons, and so it becomes more positive. Reduction is the opposite. It's gaining electrons, so your charge is being reduced, is being lowered. Memory tricks for knowing this one. By far and away, the most common one is Leo the lion goes grr. Loss of electrons is oxidation. Gain of electrons is reduction. That one's fine as far as remembering which one is losing or gaining electrons. You also need to be able to recognize them though. So make sure you recognize them by which direction the charge is going. For that, the way that I always did it was to look at the reduction one and say, oh, I'm reducing the charge. I'm lowering the charge. That one's reduced. Oh, well my other one is oxidation then. So oxidation is increasing charge. Okay, so that was the way that I remembered that direction. If you come up with new and cool memory tricks, let me know, because I'm honestly not a fan of any of the ones that are in popular circulation at the moment. Okay. So in this case, we look at sodium. We say sodium is going from a 0 to a 1, +1. Chlorine is going from a 0 to a -1. Which one is lowering in charge? Chlorine, right? It goes from a 0 to a -1. It goes in lower in charge. So is that one reduced or oxidized? That one is reduced. Sodium, on the other hand, is going from a 0 to a +1. So it's not being reduced, it's doing the opposite, which is oxidized. All right. Now, our next part here is something that we need as chemists to be able to talk about these species, to be able to say, okay, I need something that is going to reduce my compound. I have this compound, I want it to be reduced. I need a reducing agent, okay? Or I have this thing, I have this species, and I want it to be oxidized. I need an oxidizing agent. So the focus is shift a little bit. It's not, oh, this thing is being oxidized or this thing is being reduced. It's, I need something that will oxidize my thing. So when we need language for this, what we use is oxidizing agent and reducing agent, which makes a lot of sense. The thing to be careful of with oxidizing and reducing agent is that it seems a little flip-flopped if you aren't thinking about it in terms of, I am using this species, I am using this chemical to do something to the chemical that I care about. Okay? So the focus is on the chemical that you care about. I want this thing to be oxidized. I'm going to use an oxidizing reagent to do that. Now, if something is going to oxidize something else, it's going to have to be what? It's going to have to be reduced, right? It's taking away electrons from the species you care about. It's going to have to be reduced. Same thing works the other way. If you need a reducing agent, you want the thing that you care about, that species that you're talking about, the chemical that you're worried about, you want it to be reduced. You need something that will give up electrons easily to that species to reduce it. You need a reducing agent. And because that thing that is doing the reducing is losing electrons, it is oxidized. So it's flip-flopped, right? So the thing that is being oxidized is the reducing agent. The thing that is being reduced is the oxidizing agent. And again, we need that terminology just to be able to say, you know, if you're trying to do this chemical reaction and you aren't sure, you need something that'll reduce it, you can walk over to like a friend and be like, yeah, you know, I'm having this tough time with this reaction, I need a reducing agent. It's just a different way of saying I need this thing to be oxidized. Okay. Two more definitions, or one more group of definitions, and that's anode and cathode. We haven't really talked about cells yet, but may as well get this out of the way now. A lot of times we split up our reactions and we put them in different places. When we do that, it's in order to either get chemical energy out of it or put chemical energy in. There's reasons for it that we'll discuss later on. We want to be able to talk about the sides of the reaction. So for this, we use anode and cathode. Anode is where the oxidation occurs. Cathode is where the reduction occurs. The memory trick for this one is like the lamest thing ever. I don't know how it made it into everybody, but it's red cat and ox. Mine is probably even lamer. When I was doing this, I didn't like that one, so I did, oh, and ox, they're both vowels. I'm gonna put those together. Cathode, reduction, they're both consonants. I'm gonna put those together. That's pretty bad too. The memory tricks aren't particularly amazing for it, so pick whichever way you wanna memorize it and do that. This falls into the category of, I can see the thought, I'll just put it on my note card, going through many heads. It's fine. I would have had the same thought. Don't do that. The reason why, I mean, you can put it on your note card just in case you have like a during the exam freak out moment. That's fine. But know it anyways. Because when you talk about these, we're going to talk about them regularly. We're going to say, oh yeah, so at the anode, blah, 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 at the cathode, blah, blah, blah. And if every single time you have to quickly like yank out your note card and find it and be like, oh yeah, okay, this is what she's talking about, you're going to miss a lot. So commit that one to memory. It's worth spending the few minutes to commit it to memory. It's not too big of a deal. So in this case, if we had these occurring at different places, we had these two half reactions occurring at different places. This one would be a tough one to do that with, but we could theoretically. This is being oxidized, so that would be, wherever that is, that place, that would be our anode. And wherever the chlorine part of it was happening, that would be our cathode. Okay. The anode-cathode thing, this is one of those write down now for later use things. That occurs regardless of whether it is a spontaneous or non-spontaneous cell. Your anode is always your cathode. Your anode is always your oxidation. Your cathode is always your reduction. It doesn't matter what kind of cell you're dealing with. So I know we haven't talked about that yet, but it's worth writing down for later usage because it comes up a lot. Okay. So the next thing that we're going to do is learning how to actually deal with these reactions. It stalled on me a second. Okay, here we go. There's not really a recap for this one just because I would just have repeat everything I said. Make sure you can define all those and you'll be all set. Okay, now balancing these reactions. You cannot balance these identically to how you balance other reactions. There will be times where it seems like maybe you can. There'll be times where it works if you try to balance it just the normal way. Those are happy coincidences. You always, always, always need to check and make sure that your electrons are balanced as well. There's going to be two ways that we do this. One of which is the half reaction method, and one of which is, it doesn't really have a name, you leave them together and you balance it together. You can always use the leaving it together method, okay? That's the one that's universal. That being said, it is sometimes easier to split them into half reactions. So it's worth knowing the half reaction method. I know a lot of times I teach you two ways to do things, and I say pick one and stick with it. This isn't one of those times, actually. This is when you want to learn both of them. They're both really important problem-solving skills. That being said, if you really only want to know one, if you're like, no, I'm not learning two ways to do the same thing, I don't have time for that stuff, then you need to take and learn the one where you leave it together, because that one will always work, okay? And to encourage that, I promise you there will be one that if you try to separate it out on the exam, it's not going to work very well, okay? You're gonna have a mess on your hands. If you try to leave it together, it'll be simple. All right. So with the half reaction method, there's a couple of algorithms. What I mean is the half reaction method is very, very step one, step two, step three, do this, do that. Yeah, you have an answer. It's why a lot of people really like it, because you really can just put a mental checklist in, go through, do it. It becomes very habit. You can just do it with your eyes closed by the time you're done. The other way you have to do a little bit more thinking. It's actually generally easier once you get the hang of it, though. You end up with not having a half page worth of work by the time you're done, which is nice. The half reaction method, you normally end up with about a half page worth of work. So again, this will always work. This will work like 90% of the time. It works a lot of the time. This is a little more, you can just follow a checklist. This is a little more, you have to think about it, but it's easier once you get the hang of it. Okay, I'm not gonna walk through this. This is for you. Actually, yeah, this is for you. We'll walk through it really fast, but I'm not walking through it slowly enough for you to copy it down, just print off the slide. So step one, you write your oxidation numbers, and then you separate your half reactions. And we're gonna go through this really slowly with examples. You separate your half reactions. At this point, you balance everything that isn't hydrogen and oxygen. It's important, do that first. Then you balance your oxygens with water, okay? You don't worry about your hydrogens, whatever. You'll deal with that later. You just deal with your oxygens. Again, I'm going through this way too fast to write, so just print off the slide. You add H+ to balance their hydrogens, because at this point, that's really all you have left to do. And then if you have a basic solution, you do OH- equal to the number of H+ on each side. We'll do examples of this. Then step 7 is important. That's what makes this different from a normal balance. You add your electrons to balance your charges. You look at your charges on one side, your charges on the other, and you add the right number of electrons. Step 7 is the one that's easier in your half reaction method than it is in the leaving it together method. Here it's a little bit like, okay, it's just one more thing to add. In the leaving it together method, you have to think about it a bit more. You make the electrons on each half reaction equal, because you're doing this simultaneously on each reaction. And then you stick them together. So that makes no sense without an example, so let's do an example. Think of them as fun. This is like a game. It really should be kind of treated like a game. I'm just trying to get them to all work out. They're like crossword puzzle type Sudoku thing. I think they're more fun than a lot of the sort of versions of that, because it really is just kind of playing with letters. I could teach somebody who has not had any chemistry before how to do this by teaching them the rules to the game, right? And so that's kind of fun if you can treat it like that. And then also be able to explain all the chemistry behind it later on. Okay, so step one, always, and this goes for either method, do your oxidation numbers. If you don't have your oxidation numbers, you can't do anything else. So we look at this. Which one should we start with, the chromium or the oxygen? The oxygen. So what's your oxidation number on oxygen? -2, which means we have a total, how much charge on here right now? 14, -14. And how much do we want? -2. So that's a difference of how much? Instead, -14 instead of a -2. It's a difference of 12. So does that mean chromium is 12? No, because there's 2 of them. So what is chromium? All right. Next one. What is hydrogen? Not a trick question. What's hydrogen? This one. What is oxygen? -2. Now we can figure out nitrogen. I didn't go straight to nitrogen because although it is an ion that you're used to seeing sometimes, nitrogen in these sorts of compounds can have different oxidation numbers. It's why we talk about it being like an imaginary charge. It's not quite the same thing as it is when we're doing charges back in Chem 1A. So what is our charge so far? We have 2 -2s and 1 1. So at this point we're sitting at a -3, right? And what do we want to be? 0. So what does nitrogen have to be? Perfect. Toughest one of the section. What's this one? I'm kidding. It's not the toughest one of this. It's +3. Sorry, I realized that saying it that way made it sound as if perhaps it was a trick question, but it wasn't. Okay, last one. What is our oxygen? -2. So total charge right now is at -6, and we want it to be a -1. So nitrogen has to be +5. Practice doing that before moving on. Like just sit down and do oxidation numbers for a while and get the hang of it, get good at it. All right. Now let's split this into 2 things. When you're doing the half reaction method, you don't necessarily always have to be able to identify what's being oxidized, what's being reduced. That's kind of, you can solve the problem, you can solve the reaction without it, but it's a good practice to do anyways. So let's look at this. Which one is being reduced? Which one is going down in charge? Well, chromium's going from a 6 to a 3. Oxygen never really changes in this case. Nitrogen is going from a 3 to a 5. So which one's going down in charge? Chromium. It's going down in charge, so it is being reduced. What does that mean nitrogen is undergoing? Oxidation. What is your oxidizing agent? This is your oxidizing agent. This is one of those small semantic details, but it's probably worth noting it. Generally, when we talk about what is being oxidized or reduced, we talk about the actual atom. We say, in this case, chromium. Chromium is being reduced. When we talk about the agent, we generally will talk about the whole thing. And again, that just comes out of why we need those words to begin with. So we usually would say the oxidizing agent is this whole Cr2O7. Okay, so this is oxidation, so this is our reducing agent. All right, again, for the half reaction method, we don't necessarily require that. Good practice to do anyways, though. Now comes the part where we split it into half reactions, okay? So we'll split the two. We put chromate over here. I don't know why I'm writing in pink, that's a bit much, sorry. So we take this, and we put it in one spot. And then we take this and put it over here. And we treat them separately. And you can see in problems like this, that's pretty simple. They just kind of pull apart. Now we go through the steps for each one. When I do this, I'm going to kind of step down the page, just so that when you go back in your notes, you understand what's happening, and it doesn't just be like, oh, look, she went from not balanced to balanced in one step. My suggestion would be for your notes, you do the same thing that I do. When you're doing this like for real, don't just put them all together. So here's what I mean. Step 1, balance everything that isn't hydrogen or oxygen. What do we do? Put a 2 on the chromate. Now, balance your oxygens using water. Yeah, sure, that's going to mess up your hydrogens probably, but that's okay. We'll fix that later. How many oxygens do I have on this side? 7. How many on this side? 0. So what do I have to do? Add 7 waters. That's what I mean about going down a page. It just makes it easier to see what's happening. Now I have my oxygens balanced. I have everything that isn't hydrogen and oxygen balanced. All I have left is my hydrogens. How many hydrogens do I have on this side? How many on this side? So what do I need to add? Okay, so now all of my elements are balanced. Now the only thing that's left is my charges. So you add up your charges on each side. The nice part is that you know that the oxidation numbers of all the elements within a compound add up to be the oxidation number on the total compound. So all you have to do is look at the difference between this and this when accounting for the 2 here. So what is my total charge on my reactant side? Just -2. What is my total charge on this side? It's +6. So overall, what is my total charge difference? Oh, I'm sorry, don't forget this. What is my total charge over here? So my charge over here is a -2 and then +14. So what is my total charge? I'm going to put a little +12 over here. And then over here it's what? +6. So let's put those as little notes. Those are our total. So how many electrons do I need to add? 6. Am I going to add it to my more positive side or my least positive side? What's the charge on an electron? It's negative. So I want to balance my charges, so I'm going to add it to the more positive side, right? So is that the reactants or the products? Okay. Now, in this case, I'm going to do a quick rewrite, because doing this like this means it's kind of messy. So I'm just going to rewrite everything. Again, when you're doing this on your own, just, +7 here, +14 here, +6 here, it'll already be rewritten for you. It's just, this is a little easier for note taking. Okay, now we do the exact same thing on the other side. We balance everything that isn't hydrogen and oxygen. Done. We balance our oxygens using water. So how many waters do I need to add? Just one to what side? So I have how many here? How many here? So one to which side? Reactants, right? Because I need to get it up to 3. Because I'm using it to balance my oxygens, not my hydrogens. I'll deal with my hydrogens in a second. The water is there for your oxygen balancing. Now that I've balanced my oxygens, now I can worry about my hydrogens. So how many hydrogens do I have on this side? Careful. Do I have 2 or do I have 3? 3. All right. So how many do I have to add on this side? 3. Now, what is my total charge on this side? It's plus 0. And what is my total charge on this side? Careful, I have a -1, a +1, but how many pluses do I have? 3. So total I have +2, right? 3 from the hydrogen and -1 from there. So 3 minus 1 is 2. All right, how many electrons total do I need to add to get, yeah?
How did you get the +6 on the right side?
Oh, over here?
Yeah.
So over here, so let's kind of erase this for a second. I had a +14 here and a -2 here. So I had a total of +12. And then over here, I had 3 times 2 is 6. No charge here. So overall, I had a +12 over here and a +6 over here. So I need to add 6 electrons, because electrons have a negative charge. So I need to add 6 electrons to get this down to a +6. Because you're always going to add your electrons to your more positive side to reduce them down to match the other side. So going off that, how many electrons do I need to get this to be equal to each other? 2. And to which side? Products. So we add up our total charges. We had 0 and 0, which is 0. We had a -1 and a +3, which was a total of +2. To balance these, we had 2 electrons here. And now we have to do a step to balance our electrons on both sides. You can't have one giving up more electrons than the other one is taking, or vice versa. So in the one case, it's taking 6 electrons, and in the other case, it's giving up 2. That doesn't work. We need to make those equal to the same number. So it's like a lowest common multiple thing. What is our lowest common multiple between 6 and 2? 6. So we have to multiply this by 3. That should actually be up here too. We're going to multiply the whole thing by 3. Okay, rewrite time, because it's messy. This is why I don't love the half reaction method, because it does get pretty messy. So I'm just rewriting everything in a nice, neat way. Multiplying everything out. Okay. Now comes the combining process. We have everything balanced. All we have to do is mash them together and get rid of all the excess things. So first off, your electrons are always going to cancel out. If your electrons don't cancel out, there's a problem, fix it. On these, and I say this and people don't generally tend to listen to me, if I ask you for a fully balanced redox reaction, and there's electrons in your final answer, you don't get partial credit, even if everything else is right. If you have an electron in your final answer, that shows that you're fundamentally missing something about electrochemistry. The idea that if you give some electrons away, the other ones have to take it up. There's something wrong, not just in the balancing, but in your understanding of what is happening. Make sure that doesn't happen. If it happens, that just means that something's messed up. Go back and fix it, figure out what you did wrong, and move on. But there should never ever be electrons in your final fully balanced reaction. Half reactions will have them. Half reactions will definitely have them. Full reactions will not. Okay, so that takes care of the electrons. Now let's look at our hydrogens. Normally your hydrogens will have some crossing off too. So we have 9 on our product side here. We have 14 on our reactant side here. So these go away, and that becomes a 5. Okay? If you are more comfortable combining them into one reaction first and then doing the canceling out, do that. It doesn't matter which direction you do it in. I like doing this way. I like canceling it out before combining it. It causes less writing. Here we have 7 waters on our product side. We have 3 waters on our reactant side. These go away, and this becomes a, what does this become? 4. Making sure you guys are still with me. Okay, so hydrogens, waters, OHs if we need them, but we didn't really use them here. Those are your main things to check. And at that point, we're probably all right. Now we rewrite everything. So pull this down here. So quick go back, check everything, say okay, we got it, make sure everything makes sense, make sure there's nothing like, double check your waters, make sure you don't have waters on both sides, make sure you don't have hydrogens on both sides, and we should be all set. It's always good to go back as a double check and make sure that everything is actually balanced. I'll let you do that at home. Okay, that one I purposely picked to be a little bit nasty. Let's do a little bit quicker one, where I want to show you doing it in a basic solution. So we're going to do the exact same thing. Now we're going to do it in a basic solution though. So there's one extra step, that's it. And this one extra step, honestly, you can add in wherever you want. I think I put it as like step 6 or something, but you can kind of add it anytime after you've added hydrogens. Okay, oxidation numbers first. What's our oxidation number on the oxygen? Which makes nitrogen? This, what's the oxidation number on copper 2+? 2+. What is our oxidation number on this oxygen? It's always pretty much always the same for oxygen. There's like one exception. Still -2. So now that makes the nitrogen what? +5, good. Because this is -2 times 3 is a -6. But we need to make it add to a -1. So -6 plus 5 is -1. And then our copper. Okay. So these are 2 that are changing. Which one is being reduced? The copper, because it's going from a 2 to a 1. Which makes that what kind of agent? Okay, so what does that mean is happening to nitrogen? It is being oxidized, which makes it the reducing agent. Okay, now we do the same thing as we did before. We split it up. I'm going to go through this one a little bit quicker. It's also just an easier problem. So let's start with the copper this time because it's simpler. Balance everything that isn't hydrogen and oxygen. Done. Balance oxygens with water. Done. Balance hydrogens with hydrogen. Done. Add OHs as necessary. Done. Electrons. What do we have to do for electrons? Yeah, we have to add 1 electron. All right, that was nice. Okay, let's do the other one. If they don't have any oxygens or hydrogens, life is really nice for us. If they have oxygens and hydrogens, we have to do a little extra work. Okay, balance everything that isn't hydrogen and oxygen. Done. Balance oxygens, and remember, where am I getting this plan from? Oh, it's on that slide where you just kind of step through the rules. I'm just reading it out for you as we do it. Balance anything, or balance oxygens with water. So how many oxygens on this side? How many on this side? So how many do we need to add? To which side? Okay. Balance hydrogens using H+. So how many hydrogens on this side? 4. How many on this side? How many on this side? None. So how many do we need to add? But this is a basic solution. We can't have hydrogens floating around in a basic solution. So we do a step where we add in hydroxides. And we're adding in OHs, so if we don't add it to both sides, it's going to screw up both our oxygens and our hydroxides. So we add them to both sides. You can do this at any step. A lot of times it's really nice to do it after you've actually combined everything together. In this case, because this reaction isn't going to actually do much, I'm going to add it here. So I have 4 hydrogens. I don't want any hydrogens left over, so I'm going to add 4 hydroxides. Okay? Because what does this turn into? If I have 4 H pluses and 4 OH minuses, what does that actually turn into? 4 H2Os. Now, if I add 4 hydroxides to this side, I have to add it to this side. Otherwise, my balancing is going to get all messed up. So you add it to both sides. And then do a rewrite. Oh, I forgot one step in here. No one sees that. All right, now we do charges. On this side, what is my total charge between all of this? I have 0 here, 0 here, and 4 minus over here. Yeah? 4 minus over here. Over here, I have plus 4 minus 4. Those cancel out. And then what do I have right here? A minus 1. So overall, I have a minus 1 on one side and a minus 4 on the other. So how many electrons do I have to add? 3. You add them to the more positive side because the electrons are going to bring it down in charge, right? Be careful of that. The electrons are going to bring it down in charge, so you add it to the more positive side, which in this case is the minus 1. And now you rewrite. Okay. Are my electrons balanced between my half reactions? No. So what do I have to do over here? I just have to multiply by 3. Okay. Now go through, cancel everything out that is duplicated. So in this case, I actually have things duplicated within a half reaction. That will generally happen when you're in a basic solution and you're dealing with hydrogens and waters and things like that. So watch out for it. These go away, and this turns into a 2. Other than that, I don't have anything else to cancel because there's no hydroxides over here. There's no, oh, well, okay, there's always electrons, so we'll cancel our electrons. But there's no hydroxides and there's no water over here, so we're done. We just have to rewrite. And we end up with that. So this is the very, very algorithmic way. The other way of doing it, and I stepped this one out in painful step-by-step detail on the slide as well, but it's really better to just do it in a reaction. So let's do this exact same problem, but doing it the other way. This time we're going to leave it together. So if you have the slides in front of you, just go to the next slide, and that's where we're going to be walking through now. And I decided to do it on the exact same problem so that you would see exactly how much work each one is, exactly which way is your favorite, okay? So the oxidation numbers are going to be the same, so for the sake of time, I'm just going to rewrite them. Now, this one, it is absolutely required for you to right away, before you do anything else, decide which one is being oxidized, decide which one is being reduced, and decide how many electrons are being transferred. Luckily, we've kind of already done that. So we know that this one is being changed, and that this one is being changed. Need a little more room. If you need this one after class, just go ahead and check it out. Of course, the answers are online too, but I need the extra room for this one. From here to here, this is being oxidized. How many electrons are moving? From a 2 to a 5, how many electrons move? 3. And there's only one of each. So step 1 here is balance your things that are not hydrogen or oxygen first. It's already done for us, so I kind of skipped that. Once you've done that, decide how many electrons are being transferred. In this case, there's 3 electrons. How many in this case? Just 1 electron. These have to be balanced. Now, we're not going to split these ones up. What we're instead going to do is leave it together and say, I need to make those balanced. How can I make that balanced? What do I do? Times this by what number? 3. In order to do that, what coefficient do I have to add? 3. So I add a coefficient to that half reaction. Now our electrons are taken care of. Just be careful you don't mess them up somewhere along the way, or you have to go back and fix them. But at this point, our electrons are fine. Now we do everything the same as before, except that they're not split. How many oxygens do I have on this side? 1. And how many on this side? 3. So how many waters do I need to add? Plus 2 waters. How many hydrogens do I have on this side? 4. And how many on this side? 0. So how many do I need to add? We need to get rid of the hydrogens by using hydroxides, so what do? Plus 4 hydroxides, plus 4 hydroxides, and then we are done. We need to do a quick rewrite, but at this point there won't be anything to cancel. There won't be anything to really deal with in any way except for our waters, okay? We will have to deal with our waters because we did it in a basic solution. So I'm going to finish writing this if you want to stick around and watch me write it. If you need to go to class, I totally get it. So I'll start here next time.